Hello and welcome back to another LeetCode practice video. I'm currently going through the backtracking problems on neetcode.io. LeetCode has this nice little thing where you can just keep track of the problems that you've completed. And it has the LeetCode 150 list, which is an extension of the blind 75 list of curated problems that are prototypical for the different techniques that you can use to solve these coding problems, like sliding window binary tree, 2 pointers, all that good stuff. So I'm going through the backtracking problems. I have completed all of them except for the last one, so the n queens one. Yeah, and I'm just going to attempt this right now. I know that I've done this before, but that's a while ago. Let's see. Yeah, that has been 2 years ago. So I will try to solve this again. Let's see how far I get. So 51 n queens. The n queens puzzle is the problem of placing n queens on an n by n chessboard, such that no two queens attack each other. Given an integer n, return all distinct solutions to the n queens puzzle. You may return the answer in any order. Each solution contains a distinct board configuration of the n queens placement, where q and dot both indicate a queen and an empty space respectively. So the size of the board is at least 1. The max size doesn't matter because we want to do a space and time complexity analysis if we can. Yes, so here's the example. So we have a placement of queens. There exist two distinct solutions to the 4 queens puzzle as shown above. Well, okay, if we want to use backtracking, what we have to do is, if we place a queen somewhere, then we need to try to place the next queen such that it doesn't, it can't be attacked by any of the previous queens that we've placed. And the backtracking part is, well, we either find a solution or we find where a queen attacks another queen, and then we have to backtrack to adjust the previous queen, etc., etc. So these are the two solutions that exist in this example. So with n queens and it's n by n. So with 4 queens on a 4x4 grid, yeah, so queens can attack horizontally, vertically, and diagonally, right? So this is the only position where they don't attack each other. And this placement of the queens also covers all of the other fields. Every cell in the grid is now protected by a queen. So we know that we need some kind of a function to do backtracking if we want to do it recursively. We need to call that function. We need to return a result at the end. Let's see, result equals an empty list. And yeah, well, we probably should tell it which position to try, right? So we're dealing with rows and columns. If we place a queen in the first row, that means no other queen can be in the first row, right? It also means that no queen can be in the column in which we place that. So I would say maybe we iterate, well, we can iterate through the columns or the rows with the recursion. And at every level, in every row, we have n number of ways of where we could place the queen, but we have to check whether that placement is valid or if a previously placed queen can attack our queen at that position. All right, so, well, help a row. So maybe we pass in the row as the thing that we will backtrack on. And inside our function, we have to iterate over all of the columns and find a column that has not been taken yet. Right, so for call in range n. Now we have to check if call taken. then just skip it. That's what we have to do. So how do we do that? Well, I would suggest we use a hash map for that. If columns in taken columns, right? That could be a set. So if call in taken columns, we're going to continue. Otherwise, oh well, we also have to check the diagonal, right? But so we have to check diagonal. Otherwise, well, we can add this column to the taken columns, right? Oops, calls add column. And then we do our recursive call. And we do row plus 1. And then later, we remove that column again. Cool. But also we have to do the same for the diagonal as well here. Now, because I was just looking at helper, well, when do we know that we're done? Well, we know we have n rows, right? So if row it's larger or equal than n, we're done. That's when we're finished. Otherwise, we have to start iterating and backtracking. So if that is the case, we have to copy the board with all the placements. Oh, and that's another thing. So we actually have to put the placements in there as we place the queens. So to create a copy of the board, what we will do is we will we could create the board, right? Board. Oh, we don't have a board. We just have an n. So what we'll need is we need to have initialize a board as well. And that contains, well, n times n. Well, it contains these rows for in range n. Board should append a row. So yeah. So this is how we initialize the entire board. And we do our analysis here later. Time and some space. Cool. So we initialize the board, and now when we run into the edge case, we have to basically copy the board, right? So the way to do that is we iterate over all of the rows for row, well, board row in, well, actually it doesn't matter, for row in board, we have to copy it. So we create a copy of each row. We're creating a copy of all of the rows. And we append that to our result. And that is copying an entire board. That also means that when we mark a column or a position as taken, we actually have to modify the board, right? Board at position, and now first is the row, and then the column is equal to a queen, right? And after we return, what we do is we just change it back to a dot. Now we need to add the checking of the diagonal. And so we have two diagonals, right? Left to right and right to left. So we're going to need another hash set for that. Taken taken diagonals, diag equals another set. I got type today. So taken diagonals is another set. And if So we have to compute it in taking diagonals, continue. Otherwise, we're going to add this to our diagonals. So taken add diagonal. And likewise, after, we need to remove it again. And now we need to compute what the diagonal is, and it's only 1. The diagonal, how can we compute that? So when we're at position 0, 0, that could be diagonal 0. When we're at position so if x is equal to y, that could be, well, we could actually do this. X minus y, so row minus column. That means if row minus column is 0, we're going to be on this diagonal right here. If the row minus column is minus 1, reverse this. If we're in the column 0 and in row 1, that's here, then this is diagonal 1, minus 1, sorry. However, when we are in column 1 and row 0, that is diagonal 1. So we have minus 1, 0, 1, 2, 3. So we have basically all of these columns. But we also need to describe this, the perpendicular diagonals to that. So we want this to be maybe a second diagonal. Diags, maybe we have 2 sets, because we have 2 sets of diagonals. Add diag 1, diag 2. Well, actually, no, that's not how that works. 0, add diag 1. And then in the second one, we're going to add diag 2. And we also need to remove them later. And so we compute diag 1, and we need to compute diag 2. So diag 2 is now something else. So we want this to be the 0, this to be the 1, and this to be the 2. So when is this 0? When they are equal, then it's 0. But this is 1 when one of them is 1 and the other one is 0. This is 2 when one of 0 and 1 is 2. One is 1, both are 1 or the other way around. So the second diagonal is just the addition of them, if they're both the same. Cool. So we're going to add those little checks here. Cool. Diag 1, diag 2. This looks like a lot of code, but this is, I think, how we should check it. Alrighty, so let's run through one example. So helper 0, we call our little helper function row 0. The row number is not larger or equal to n. So we're going to iterate over the columns. We're going to try to place the first queen here at position 0, 0, right? And everything should pass. We should not run into any continuous here or whatever. We're going to add column and row 0 as well as this diagonal and this diagonal to the occupied territory, so to say. And yeah, we mark this position with a Q as a queen. Now we call the recursive helper function. We go back in again. We now try to place the queen in the first in row with index 1, which is the second row in our grid. So in the beginning, we're going to try to place it exactly at column 0. But because column 0 is already in the taken columns, we're going to continue. Then column becomes 1 for the index 1. And we can place it because it's on the same diagonal. So then we go here and we actually can place the queen here. Right, now we go into the recursive call. We can place the next queen here. We cannot place it here because this is where the queen is. We cannot place it here because there's a queen and there's another queen. And we can't place it here because there's a queen. So we couldn't place a queen at all. So now we're backtracking and to our first placement of the queen. Now we place D and then blah, blah, blah. We go all through this. So I think that should work. Let me just go through the test cases before I do the time and space analysis. Taken diag is not defined, right? Because we renamed it. Taken diags. Right. Let's try again. Rows is not defined. Rows is not defined because I used the variable name row here. Let's try again. And we're getting the wrong answer. Oh, so here they combine actually the characters in the row. Was that specified? Oh yeah, I just didn't look at the example. So what we do here is we just join the characters in the row, and that should fix that. Cool. So the 2 test cases pass. Let's submit this. Oh, surprise. So that works. Nice. So in terms of complexity, well, this is an interesting one because let's see. So we have, because this is an n by n, we have n ability. Well. In terms of space, I don't know if there's a formula for the number of correct spacings, but the space is definitely n by n. That's for every board times however many boards we find, right? And the recursion is also, the depth is also only n. But if we look at our time complexity, we know we're iterating over n rows. We're also iterating over n columns. Right, n columns. However, that is not how that works as far as I know, right? So we still have to consider well, how do we get there? Yeah, I need to make a video about this where I explain to myself how to do the runtime complexity analysis with backtracking when we have a branching factor, when we have choices to make. Looking at the other examples that we have, I believe that we'll have something n factorial, something. That's probably what we're looking at here. What could be an upper bound? I mean, in the worst case, like if we can't find a timed upper bound, maybe we can find a bad upper bound. So in the worst case, we place the queen, well, we have n ways of placing the queen in each row, right? And we have n rows to go through. So that tells me that should be something with n factorial. Yeah, so naively thinking, if we place the queen in one position, we have n ways, n minus 1 ways to pick the next, then n minus 2 ways to pick the next position, etc., etc., etc. But inside our loop, we're iterating over n elements. So I think we'll have an n here as well. That's what I think. And so that would be an upper bound as well for the number of results. So it's not a, well, we have n by n elements on the grid. At how many different placements? Well, we have n queens, but we have n squared different cell positions. So how many different ways are there to place n queens on n squared positions? That could be a worst case time complexity analysis. I really have to review the stuff. So sorry for rambling. Maybe we can find something here in the solutions. N queens. What does this person have? It has backtracking explores n factorial states. Overall n squared n factorial. Chessboard is n squared. Recursions O of n. Overall O of n squared. But that's not true. If the board alone is n by n, and we can find n boards, that would be n cubed, wouldn't it? And at least n cubed would be an upper bound, even if it's not a tight upper bound. General approach for all backtracking, blah, 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 blah. Do we see... Oh, maybe I should read this one. General approach. I feel like the people who use all these emojis, they're probably the ones who put in the effort to make a runtime complexity analysis, etc. I feel like everybody's just YOLOing that part. So it's probably worth to figure out really well how to do these runtime space complexity analysis for these backtracking things. Yeah, but that's for another day. I'm happy that I've solved this one now. And I can complete the backtracking list. Very nice. So yeah, thanks for watching. I hope you learned something, or at least I inspired you to try yourself and don't be ashamed when you can't solve everything or some parts are wrong, just as in my videos.